Recall that we found that the sample mean x bar was 2.2 ppm, and we want to validate whether this mean of the sample will actually be the mean of population. Now we understand one thing for sure. To find out the population mean exactly from the sample mean with zero error is near impossible. We'll obviously make some error. That is, at the best we can say that the population mean should be 2.2 plus minus some error. So we might be able to conclude that the population mean will be 2.2 ppm plus minus 0.1 or 2.2 ppm plus minus 0.2 or something like that. But that is still useful to us. The aim of the problem at hand is to be able to tell whether the amount of lead in a noodle packet is greater than or less than 2.5 ppm. So even if we can say that the mean of the population is 2.2 ppm with an error of plus minus 0.2, we would know for sure that the mean lead content will be between 2 and 2.4, which is definitely less than 2.5. Now, in order to see if the sample is indeed a true representation of the population, let's do a simple experiment. Let's go back to our noodles example where we already have a population whose parameters are known to us. Consider that you have the complete set of 30,000 noodle packets that this company has manufactured. We are given that capital N is equal to 30,000. Now each data point in this CSV file is the lead content in ppm for that noodle packet. Now if we check the mean of this data, we get it as 2.199 and the standard deviation comes out to be 0.132. These are population mean and standard deviation values, which are represented as mu and sigma respectively. But for now, let's take a small sample size of 5 and see what its parameters are. So we randomly choose 5 noodle packets out of 30,000 and we find out that the mean of their lead content is 2.145 ppm. But this is a little far away from the actual population mean, which was 2.199. It might have happened that we coincidentally choose noodle packets with lower lead content. Let's take another example. This time the mean comes out to be 2.27 ppm, which is quite higher than the population mean. Again, it's look like we coincidentally choose noodle packets having higher lead content. So to normalize this effect of getting biased samples, let's choose 100 samples instead of 2. This number could have been 70, 80 or 90, but for now let's move with 100 samples. Note that we are talking about number of samples here and not the sample size. Sample size here is still 5. If we plot these sample means on a graph, we find out that the distribution of these sample means looks like a normal distribution. And if you see the center point of this distribution, it is around 2.2, which is in fact very close to our population mean. This certainly opens up many avenues. We saw that when we took a large number of samples and plotted the mean of each sample on the graph, we got a distribution that was quite close to a normal distribution. As we keep on increasing the sample size, the sample mean will keep approaching the population mean. Now, when I say increasing the sample size, I mean the number of noodle packets in each sample and not the number of samples that we took. So earlier our sample size was 5. If we increase it to 10, keeping the number of samples the same, that is 100, the distribution becomes thinner and closer to a normal distribution. In fact, if you keep increasing the sample size, the distribution keeps getting narrower and the distribution seems to look more and more like a normal distribution. In fact, when you increase the sample size to 30, it becomes almost perfectly normally distributed with the mean centered around the population mean. What does this mean for us? This experiment that we performed right now is the basis for central limit theorem. The central limit theorem states that when you take a large number of samples, the mean of the sampling distribution thus formed will be approximately equal to the population mean. The second part of the theorem states that the standard deviation of this sampling distribution will be equal to sigma, which is population standard deviation, divided by the square root of n, where n is the sample size. Just remember that the sampling distribution standard deviation would be sigma by square root of n. Finally, the central limit theorem states that if the sample size that you take is greater than 30, the sampling distribution will become normally distributed. These three findings, in short, constitute the central limit theorem. Let us first look at a few terms and notations. The whole bunch of packets, that is 30,000 packets, is called the population. And the small collection of packets that we select from it is called a sample. If you look at this table, you can find all the notations and formulae for both the population and the sample. The population size is denoted by capital N, its mean by mu, and its standard deviation by sigma. The variance in turn is sigma squared. The formula of the sample have a small twist here. The sample size is denoted by lowercase n and the mean by x bar. which is nothing but the sum of all the observations in the sample divided by the total number of observations, which is the standard way of computing the mean. So there's nothing different about calculating the mean for the sample. This X bar, after measuring the lead content, was found to be 2.2 ppm parts per million. But now, if you come to the sample variance S squared, you can see in the denominator you have n minus 1 instead of n. To concretize your understanding of the central limit theorem, let's try and visualize the central limit theorem. We plot means sampled from a non-normal population with 100 samples for different sample sizes. The 4 plots corresponding to our 4 sample sizes are 1, 5, 10 and 30. Examine the 4 density plots for the sample that are colored in blue and compare with the normal density distribution in red here. We start with a sample size of 1. The resulting curve deviates a lot from the red curve. As we keep on increasing the sample size from 1 to 5, 10 and 30, the blue curve comes closer and closer to the red curve. This graph is now starting to look like a normal distribution, and the reason for this is the central limit theorem. And what this states is that if you plot the sampling distribution, then this distribution approaches a normal distribution regardless of what your parent population is. And this is especially true when the sample size is above 30. So here you can see that even with a sample size of 30, the distribution almost approximates a normal distribution. If you look different means from different sample sizes, they appear to be similar. You see that this is also the mean of the population. And then you come to the third graph, and here you see that this is the mean of the sampling distribution. And you can see that both these means are almost equal. The standard deviation of sampling distribution is the standard deviation of population divided by square root of sample size. As you keep on increasing the sample size, the curve will start to look like normal distribution. Now, as you increase the size of n, you are bringing the n value closer to the population size value. You will start seeing that the sampling distribution of sample means will start looking more like a normal distribution, and you see that the mean is becoming more equal to the population mean. What about the standard deviation of the sampling distribution? Compare the standard deviation value of the population, which is 28.80, with the standard deviation of the sampling distribution. The standard deviation of the sampling distribution approaches closer to the standard deviation of population divided by the root of n. For example, the standard deviation of sampling distribution for n equal to 30 is 5.3, which is closer to 28.8 upon root 30, which is equal to 5.26. Also see that the normal distribution became thinner as the sample size increases. This is because the standard deviation decreases. Remember here, the standard deviation is sigma by root n. So obviously sigma by root 5 is going to be higher as compared to sigma by root 30, which is why this graph seen earlier becomes more packed. And now, what do you think will happen if I further increase the sample size, say from 9 n equal to 30 to n equal to 50? The normal distribution will become even narrower, right? So this is your central limit theorem. Statistical Inference 2, Introduction to Confidence Intervals. Let us go back to the noodles example and see if we are able to derive conclusions about the population using the sample. If you recall, we took a sample of 100 packets and find out that its sample mean was 2.2 ppm and standard deviation was 0.7 ppm. Making use of what you learned about sampling distributions, we can directly assume that this sample mean of 2.2 ppm that we have calculated belongs to one of the infinite possible sample means that is present in the probability distribution. And this probability distribution is nothing but our sampling distribution. Remember that the sampling distribution is nothing but the distribution of all the possible sample means that can be generated from this population. And this means that our sample mean, which was 2.2 ppm, is definitely one of the sample means present in this distribution. As per the central limit theorem, if the sample size is greater than 30, then we can assume that this sampling distribution is normally distributed with mean equal to the population mean, which is unknown in this case, and standard deviation equal to sigma by square root of n, where sigma is unknown and n is the sample size. So with this, we can conclude that our sample mean, which was 2.2 ppm, belongs to a normal distribution with mean equal to the population mean and standard deviation equal to sigma by root n. Again, this distribution is called the sampling distribution, and the reason we know that this sampling distribution will be a normal distribution is because of the central limit theorem. So the sampling distribution is like this, and our sample might lie somewhere in this distribution. So let's start with the estimation. Right now, we know that the mean of this normal distribution is equal to mu, which is the population mean. but we don't quite know what this mean is. So let's come back to that later. This distribution standard deviation is sigma. Now remember that sigma is the population standard deviation, but wait, we don't know what the population mean is. How are we supposed to know the population standard deviation? Now there may be some cases where prior to sampling, you were able to obtain a good estimate about the population standard deviation. In that case, you can use the value of sigma as it is. But what if that is not the case? In fact, in most practical scenarios, such as our nodal example, sigma is usually unknown. In such cases, we'll need to substitute the sample standard deviation in place of the unknown population standard deviation sigma. The sample standard deviation is represented by S, and which we found out to be 0.7. Hence, replacing S in the formula and replacing N with 100, which is the sample size, we get the standard deviation of the normal distribution as 0.07. Note that here we are using the sample standard deviation as a substitute for the population standard deviation. This is something we do since in most cases we will not know the population standard deviation. Now come back to our example. We know that the distribution is normal, and thus we can make use of the different properties that we have learned about the normal distribution. Recall that one of them was the empirical rule, also known as 1, 2, 3 rule. So let's quickly revisit that rule. The probability of x lying between mu minus sigma and mu plus sigma is around 68%. 1. 2. The probability of x lying between mu minus 2 sigma and mu plus 2 sigma is around 95%. And 3. The probability of x lying between mu minus 3 sigma and mu plus 3 sigma is 99.7%. Using this rule, we can say that the probability that the sample mean, which is 2.2, will lie between mu minus 2 standard deviation to mu plus 2 standard deviation will be equal to 95%, right? Note that mu is the population mean, and it is the same as the mean of the sampling distribution, which we are making use of. Standard deviation is something we just found out using sigma by root n, which we calculated as 0.07. So going back to our problem, we said that 1, 2, 3 rule states that 95% of the values in a normal distribution lie between mean plus minus 2 standard deviations. We do know that the standard deviation of this normal distribution is 0.07, which we just found out. Hence, this equation after replacing 0.07 becomes probability of mu minus 0.14 is less than 2.2, which is less than mu plus 0.14 equal to 95%. That is, probability of 2.2 lying between mu minus 0.14 and mu plus 0.14 is 95%. Now using this equation, can you tell what will be the value of mean mu lying between 2.2 minus 0.14 to 2.2 plus 0.14? Think about it. It's the same thing. You simply just rearrange the terms of the expression probability of mu minus 0.14 less than 2.2 less than mu plus 0.14. So you got the expression probability of 2.2 minus 0.14 less than mu, which is less than 2.2 plus 0.14. What we did was we simply carried over mu to this side and 2.2 to either sides. So since both of these are the same equation, you can say that probability of 2.2 minus 0.14 is less than mu, and mu is less than 2.2 plus 0.14 equal to 95%. Or in other words, probability of mu being lying between 2.06 to 2.34 is 95%. Hence, you can say that with 95% probability that the mean will lie between 2.06 to 2.34. And you found out this value just by using the 1, 2, 3 without even knowing the value of mu. So before moving further, let's get some terms straight. The probability associated with this claim is called the confidence interval. In this case, since we are concluding about the population mean with 95% probability, we can say that the confidence level is 95%. In many cases, instead of confidence level, you may also be given the level of significance, which is denoted by alpha. The significance level is given by 1 minus confidence level. So if the confidence level is 95% or 0.95, then the level of significance will be 1 minus 0.95, which is 5% or 0.05. Similarly, if you are given the level of significance or told that alpha is equal to some value, say 0.05, then you can say that the confidence level which we want to conclude is going to be 95%. Next, you have the margin of error, which is the maximum error made in the sample mean. In this case, margin of error is 0.07 into 2, which is 0.14. And finally, the final interval of values that you get is called the confidence interval. In this case, our confidence interval is 2.06 to 2.34. The upper bound of the confidence interval, that is 2.34, we can conclude that the noodles that are being manufactured on average do not contain higher than the accepted threshold of lead, which is 2.5 ppm. And we did all of this using just a sample of few noodle packets, which is amazing, right? Hi, welcome to the Statistical Inference 3 Confidence Interval Construction. If you look back at everything you learned till now, it was all about solving a simple problem, calculating an interval for our population mean. And in order to do this, you learned something about sampling, sampling distributions, central limit theorem, and many other things. So in this discussion, let us actually generalize this approach so that if we give us any large population and ask us to give an estimation about the population mean, we know how to solve this problem and come up with an unbiased confidence interval. First, you need to decide whether it is practical to actually obtain all the values in the population so that you can calculate the mean accurately, because in such a case, your problem is already solved. But suppose getting this population data is not actually feasible at all, which is usually the case. This is where your inferential statistics knowledge comes into play. There is no way to know the actual population mean and standard deviation. So for this population that we have with us, we said its mean is mu and standard deviation is sigma. And the objective of this problem is to get an estimate of the population mean, that is mu. Also, most important of all, this population can follow any distribution. It need not be a normal distribution. It can be a uniform distribution or any random distribution that comes to your mind. So how do you start this problem? You start by collecting a sample, right? You have even learned multiple sampling techniques such as simple random sampling and stratified sampling. So it is up to you to choose an appropriate sampling technique, such as that whatever sample you have can be considered a proper representation of your population. So let's say you have selected your sample with a size of small n. Now for this sample, calculating various parameters such as mean and standard deviation are possible. So let's calculate those. Let's call the sample mean as x bar, sample standard deviation as s, and sample size as n. Now remember that we know the values of x bar, s, and n, and using these values, we need to somehow find an interval for our population mean mu. To solve this problem, you learned that we can make use of central limit theorem. Let's recall this theorem. The central limit theorem is based on a probability distribution known as sampling distribution. So firstly, what is this sampling distribution? Let us say we have our population and we start collecting different sample of size n. And let's say you collect your first sample, calculate the sample mean, call it x bar 1. Then calculate your second sample, calculate the sample mean, call it x bar 2, and so on. Now you can continue this process an infinite number of times and you'll be left with an infinite number of sample means that are x bar 1, x bar 2, x bar 3, and so on, all the way up to x bar infinity. Now suppose you consider your random variable x such that it is the sample mean, then the possible outcomes of x will be x bar 1, x bar 2, x bar 3, and so on up till x bar infinity. Then the probability distribution that this random variable x follows is called sampling distribution. You will also hear some people saying it sampling distribution of sample means, which is the same thing. So we have this sampling distribution. Now our central limit theorem says that this sampling distribution that you have generated is going to be more and more like a normal distribution as you increase the sample size n. In fact, we assume any sampling distribution as a normal distribution if the sample size is greater than 30, which has a mean of mu and standard deviation of sigma by root n. We have selected our sample, whose sample mean is x bar and sample standard deviation is s, and the sample size is n. Now using these values, you need to come up with an interval for our population. Now if we consider a confidence level of y%, and if we apply the central limit theorem, we can derive that our population mean lies in the range x bar minus z into s by root n plus x bar plus z into s by root n, where z is the critical value associated with y% confidence interval. For example, if the confidence level at which you are looking to estimate the population parameters is 90%, then the value of z will be 1.65. If the confidence level is 95%, then the value of z will be 1.96. And for 99% it will be 2.58. These are the standard z values for confidence levels traditionally taken in the industry. You can choose the confidence level according to your problem. For example, in our noodles problem, we want to be highly confident in our results since the entire company's business depends on this. And hence, in such cases, choosing a confidence level of 95% or 99% makes more sense. On the other hand, if you are even 90% confident that making a change in your homepage will result in generating more leads, you can probably go ahead with it and make the change. So based on different scenarios, you choose different confidence levels. To make it easy for us to remember, there are 5-step approach that you can use for estimating the mean of a population. First, you collect a sample of size n greater than 30 from a population. In step 2, then you compute the sample mean x bar and sample standard deviation. In step 3, now you can assume that your sampling distribution is a normal distribution with mean equal to population mean mu, which is unknown, and a standard deviation sigma by root n, which can be approximated by s divided by root n. Step 4, you select the confidence level at which you want to estimate the population mean. For example, 95%, 99%, or maybe 90%. It can be lower or higher than these numbers based on your requirement. Finally, compute the confidence interval given by x bar minus z into s by square root of n to x bar plus z into s by square root of n. Now that you know how to determine the confidence interval for a population, we'll take a look at some other scenarios that you might come across and learn how you can calculate the confidence interval for these scenarios. Statistical inference 4. Interval estimation for small samples. So far, you had the luxury of collecting lots of data points, which meant your sample size was at least 30, which allowed you to apply the center limit theorem. Hence, you need a minimum sample size of 30 to be able to use the Z distribution for calculating the confidence interval. However, in real life, you'll often come across situations where you have to work with small samples. For example, assume you are working for a pharma company. You need to compute an interval for the effect of a medicine on patients, and you only have 15 volunteers. In such cases, it is better to use the T distribution when the population standard deviation is not known, instead of using the Z distribution, where we estimate the population standard deviation to be equal to the sample standard deviation. So in this discussion, you will see how to calculate the confidence interval using a T distribution when your sample size is less than 30. So first, let's understand what this T distribution is. The T distribution is centered at 0, but its standard deviation is proportionally larger compared to the Z distribution. The only difference is that the T distribution has a shorter peak and wider tails. Consider the figure shown here. The exact shape of T distribution depends on the size of sample. For smaller sample sizes, the T distributions are flatter, and for large sample sizes, as you can see here, how the sample size relates to the T distribution. As sample sizes increase, degrees of freedom increase, and as they approach 30, the T distribution approaches to normal distribution, which is in black. So let's take an example where you can understand how you can estimate the interval for smaller samples. Imagine you work for a pharma company and are testing the effects of medicine on 15 volunteers. Hence, your sample size is 15. Now you find that medicine increases the presence of a particular hormone XYZ in patient's blood by 10.038 microunits. So this value becomes our sample mean. Since the population standard deviation is not known to us, we estimate this using the sample standard deviation. Let's say that our sample standard deviation comes out to be 0.072. So how do we solve this problem? Recall the general approach you learned for estimating the interval using Z distribution. We will use this exact same approach except for a few changes. So let's go over each step that you have learned. The first step was to collect a sample size n. Here n is equal to 15. Since the sample size is less than 30, we'll go ahead with the T distribution. Let's move to step 2. Now step 2 was to compute the sample mean and standard deviation. Since the population standard deviation is known to us, we are estimating this with the sample standard deviation. Again, the values of sample mean x bar and the sample standard deviation s is 10.038 and 0.072. Coming to step 3, earlier you learned that step 3 was where we assumed our sampling distribution was a normal distribution. However, since we are dealing with a smaller sample, hence in our case the sampling distribution will follow the T distribution. Now, like the normal distribution, there is an entire family of different T distributions. Each T distribution is distinguished by what statisticians call degrees of freedom, which are related to the sample size of the dataset. For a sample size of n, the degrees of freedom for the corresponding T distribution would be n minus 1. For example, for a sample size of 100, the T distribution would have 100 minus 1, that is 99 degrees of freedom, denoted DFT99. This is why for smaller sample sizes, the T distributions are flatter than for large sample sizes. In fact, as the sample size increases, the degrees of freedom also increase. This makes the T distribution look more like a standard normal distribution or the Z distribution. The point where they become very similar to each other is about the point where the sample size is 30. Hence, for any sample size that is greater than 30, the T distribution can be approximated to a normal distribution. So, in our case, the sample size is 15. This means that the degrees of freedom should be 15 minus 1, which is 14. Hence, the distribution that we will use to calculate the confidence interval will be a T distribution with degrees of freedom equal to 14. Now that we know our sampling distribution for step 3, let's move to step 4. If step 4 was to select the confidence level at which you want to estimate the population mean, let's assume that the confidence level we want to estimate is 95%. Let's move to step 5. This is the step where we calculated the final confidence interval using the formula x bar minus critical z multiplied by s by square root n. The only difference in the formula will be that in place of z, we use t value. The confidence interval for our population mean will thus be given by x bar minus critical t times s by square root n to x bar plus t critical times s by square root n. So what is the t critical value? To calculate this value, we'll use either the t table, or you can also compute t values on t table easily using our software. So we are going to search for 0.05 significance value and two-tail test. For now, we do not have to worry about what is one tail and two tail. We select the critical t values from the table corresponding to the degrees of freedom. For example, in this case, degrees of freedom is 14. So we'll find the critical value as 2.145. The lower bound of the interval will be x bar minus t critical into s by square root of n, and the upper bound of the interval will be x bar plus t critical times s by square root of n. So let us substitute the values we have, and then we get 10.038 minus 2.145, which is our t critical times s, which is 0.072, and then divide by square root of 15. This comes out to be 9.998. Similarly, the upper bound will be 10.038 plus 2.145 times 0.072 divided by square root of 15, and this value comes out to approximately 10.077. So we can say that our confidence interval for the presence of that hormone lies in the range of 9.998 and 10.077 with a 95% confidence interval. So let me quickly recap what you have learned in this video. You must use the t-distribution bin, the number of data points that is a sample of size of less than 30, and the t-distribution is also preferred when the population standard deviation is unknown. You also learned that the t-distribution depends on an additional parameter called degrees of freedom, that is df. The degrees of freedom is calculated as a sample size minus 1. As the sample size increases, it means that the degree of freedom is also increasing, and as a result, the t-distribution tend to become narrower and narrower. At sample size greater than or equal to 30, the t-distribution is essentially indistinguishable from a normal distribution. Which is why if you tried solving the noodles problem using the t-distribution, you will get the same result as you got with the z-distribution. So going forward, we can see that the flowchart that you can use for deciding between z and t-distribution. If the population standard deviation is unknown and the sample size is greater than or equal to 30, then z-distribution is perfect over t-distribution. This is so because t-distribution approximates the variance using the sample size, as you saw when we increase the degrees of freedom. But this is not the case with z-distribution. However, if the sample size is less than 30, then even if the population standard deviation is known, it is best to use the t-test as it is ideally suited to dealing with a small sample. Now if you use the t-distribution, then there is the formula for calculating the confidence interval. The lower bound of the interval is given by x bar minus t into s by square root n, and the upper bound is given by x bar plus t critical times s by square root n. Now using z-distribution and t-distribution, you can estimate the confidence interval for any sample, whether the sample size is greater than 30 or less than 30. Statistical Inference Part 5, Interval Estimation for Proportions. Here we have assumed that all the values in our sample are numerical values. But what if the values are categorical in nature? A very common example of this is the exit polls that are conducted during the election. The idea of these polls is to estimate the number of people who voted for a certain candidate or party. Suppose you sample a few voters and calculate the proportion of voters that voted for a certain party. Now how will you extrapolate this value to the entire population? In this discussion, we'll show how to solve such problems, and as an example, we'll take up this exact problem. In this discussion, we will show how to solve such problems when the data is categorical in nature, and in such cases, we calculate the proportion instead of mean. Let's see this example. If you're working as a part of political science company that specializes in voter polls and designs surveys to keep political office seekers informed of their position in a race. This is done through telephone surveys where they ask registered voters who they would vote for if the election were held at that day. Now suppose there is an election campaign going on, and through these interviews, you found that 220 registered voters out of 500 contacted favor a particular candidate. Now your company wants you to develop a 95% confidence interval estimate for the proportion of the population of registered voters that favored that candidate. As you can see, the data in this problem is categorical in nature. Either the voter voted for that candidate or did not vote for that candidate. For this reason, we'll work with the proportion of voters that voted for the candidate. Hence, the proportion of voters who voted for the candidate is 220 divided by 500, which is 0.44. Now, the objective here is to compute a confidence interval for the sample proportion value, which is 0.44. The idea is to compute an interval around 0.44, for example, 0.43 to 0.45. Let us call this sample proportion as p bar equal to 0.44. As we mentioned earlier, the approach for solving any interval estimation problem remains always the same. Let us go back to our 5-step approach that we discussed earlier and understand how we can solve this problem. Step 1 here is to collect a sample of size, and as you can do that, in our case sample size is 500. Step 2 is to calculate the sample mean and standard deviation. However, since our data is categorical in nature, we only have data on sample proportion. We found the sample proportion to be 220 by 500, which is 0.44. Step 3 was to assume our sampling distribution as normal distribution. Now, as you have learned, for any interval estimation problem, we derive the interval from the sampling distribution. When we use the normal distribution, we first generated the sampling distribution of sample means, which was x bar. And we found that the sampling distribution was a normal curve with parameters mu and sigma by root n. In our example, since we want to find the interval estimate for the population proportion, if you recall the condition of approximating the sampling distribution of sampling means, it was that the sample size should be greater than 30. Similarly, we have a condition for being able to apply the sampling distribution of sampling proportion. The condition is that first, the sample size, which is n, times the population proportion p should be greater than 5. And second, the sample size n times 1 minus population proportion p should be greater than 5. So let's see if these conditions are satisfied. Now, since the best estimate of the population proportion that we have is the sample proportion, hence we'll substitute the sample proportion in the equation. Since we know n equal to 500 and p is approximately 0.44, we already know that np equal to 220. Similarly, if you calculate n times 1 minus p, it will come out as 280. Since both these values are significantly greater than 5, we can say that our sampling distribution follows a normal distribution, and we can go ahead and use the formula for the confidence interval of the population proportion, as we'll see shortly. So let us move to our step 4 for now. Step 4 was to select our confidence level. It has been given to us that the company wants us to develop a 95% confidence level for the proportion. Finally, we come to step 5, which is where we compute the final confidence interval. For calculating the confidence interval, we'll use the formula given by p bar minus critical z times the root of p bar into 1 minus p bar by n, as shown here. So this is the lower bound of our interval, and the upper bound of the interval will be p bar plus critical z times under root p bar into 1 minus p bar by n. Just by looking at the formula, you can say that the sampling distribution that we have used is a normal distribution with mean as the sample proportion and the standard deviation as the root of p bar times 1 minus p bar upon n. You already know that p bar is equal to 0.44 and the sample size n is 500. We also have to calculate z, but you have already learned that for a 95% confidence interval, z will be 1.96. So let's put these values. So if I just look at the margin of error z, or critical z times root of p bar into 1 minus p bar by n, and putting in the values, we'll get this values 1.96 times root of 0.44 into 1 minus 0.44 upon 500, which is equal to 0.3965. Overall, the value will give us 0.44 minus 0.0435 equal to 0.3965, which is the lower limit, and 0.44 plus 0.0435 equal to 0.4835. So our confidence interval is 0.3965 to 0.4835. Thus, we can conclude that there are 95% chances that the proportion of all voters that favor the candidate is within range of 0.3965 to 0.4835. So now let us quickly go over the approach for solving the interval estimation for the population proportion. Wherever the data is categorical in nature, we calculate the proportion instead of mean. So the aim of the problem is to be able to estimate an interval around the sample proportion p bar. To start off, these are n times p bar should be greater than 5 and n times 1 minus p bar should be greater than 5. If both these conditions are met, then we can use the formula for inference. This formula is given by quite simply p bar minus z times root of p bar into 1 minus p bar divided by sample size n. Here z is basically your critical z value that will depend upon the confidence level that is provided to us.